we want to determine the limit as x approaches positive infinity of the rational function, the quantity 2x plus 3 divided by the quantity x squared minus 4x plus 5. When determining limits at infinity of rational functions, we can tell a lot about the limit by determining the degree of the numerator and the degree of the denominator. So in this case, notice how the degree of the numerator is 1 and the degree of the denominator is 2. So the degree of the numerator is less than the degree of the denominator. Now let's look at some notes. If the degree of the numerator is less than the degree of the denominator, which is our case, then the limit of the rational function is going to be 0. So based upon this shortcut, we know our limit is going to be equal to 0. But let's also review the other two possibilities. If the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is equal to the ratio of the leading coefficients. And if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. So going back to our limit, because the degree of the numerator is less than the degree of the denominator, this limit is going to equal 0. There are a couple ways of explaining this. First, because the degree of the denominator is higher than the degree of the numerator, the denominator is increasing faster, or it's winning the race to infinity, and whenever we have a fraction where the denominator is increasing faster than the numerator, the function value is going to approach 0. But there's also a general guideline that we can follow to determine limits at infinity of rational functions. This general guideline is we want to divide each term in the rational function by the highest power of x in the denominator, and then once we do this, the new form should help us determine our limit. So looking at our limit, because the highest power of x in the denominator is x squared, we'll go ahead and show this by dividing every term by x squared. So we'd have the limit as x approaches infinity of 2x divided by x squared plus 3 divided by x squared divided by x squared divided by x squared minus 4x divided by x squared plus 5 divided by x squared. Now we'll go ahead and simplify each term. 2x divided by x squared would be 2 over x. 3 divided by x squared stays 3 divided by x squared. And then in the denominator we have x squared divided by x squared, that's 1. Minus 4x divided by x squared would be 4 over x. Then finally plus 5 divided by x squared. Now we need to consider how each term behaves as x approaches positive infinity, which brings us to one of the basic ideas when determining limits at infinity of rational functions given by this definition here. The limit as x approaches infinity or negative infinity of c divided by x to the power of r is always equal to 0 when r is a positive rational number and c is any real number. This is telling us that in fraction form, if the numerator is a constant and the denominator is increasing or decreasing without bound, that function value is always going to approach 0. To illustrate this, we can take a look at two basic rational functions as we see here. F of x equals 1 divided by x and f of x equals 1 divided by x squared. Both of these functions fit the form given here where we have a constant divided by x raised to a positive rational power. Notice for both graphs, as x approaches positive infinity, the function values approach 0, and as x approaches negative infinity, again, the function values are approaching 0. So going back to our example, let's consider what's happening to each term as x approaches positive infinity. Well, 2 divided by x would approach 0. It fits this form here. 3 divided by x squared would also approach 0 as x approaches infinity. Then looking at the denominator, notice how this 1 is not affected by x, but 4 divided by x is going to approach 0, as well as 5 divided by x squared. So the numerator is approaching 0, the denominator is approaching 1. Therefore, our limit is equal to 0, which we already knew by determining the degree of the numerator and denominator. And finally, to confirm our results, it's always a good idea to graph the rational function. So we'll go ahead and do that. Here's the graph of our function. As x approaches positive infinity, we're moving in this direction along the graph, and notice how we're approaching the x-axis, and therefore the function values are approaching 0. And remember, because this limit does equal 0, this is also telling us that our graph has a horizontal asymptote of y equals 0. Okay, I hope you found this explanation helpful.